For years, you've been taught about electron orbits, electron energy levels, and things like that, and you're just told that they exist. Fair while ago, Bohr actually did some calculations around it, and he came up with a model of these fixed energy levels that electrons could exist in. I'm not going to do it the way that Bohr did it. In fact, Bohr kind of had to make some guesses and didn't get it right necessarily, or he made assumptions that meant he could have been wrong. What I'm going to use is A-level physics to prove this process and basically calculate orbit radiuses of electrons around nuclei. So, to start off then, we're going to have to use quite a few different areas of physics. The first bit we're actually going to be looking at is going to involve circular motion. It will involve Coulomb's law. And we're going to make the good old assumption we often make that we've got point charges in terms of all of our calculations or all of our considerations. Now, what does that mean? Well, what we've actually got set up then is we've got some positively charged nucleus, and we've got to assume we've got a circular orbit around, and we're going to say, well, that distance from there to there is the radius r of this orbit. And there's our electron actually whizzing around on that orbit. Now, from circular motion, we know that F must be equal to mv squared upon r. But we also know that that force must be provided by Coulomb's law, the force of attraction between the positive nucleus and the negative electron. So that must be equal to 1 upon 4 pi e naught q upon r squared. Now, to make this 100% clear, I'm going to use this as the big Q, the charge on the nucleus. This is the little q, the charge on the electron. And the mass we're talking about here is the mass of the thing in orbit. So the mass is actually the mass of the electron. Okay? So quite a standard problem in terms of A-level, in terms of equating the force to the circular motion. So that's our first chunk. Actually, I want to simplify it just a little bit first. So let's actually have a look at what I can do. If I look at this, I can obviously cancel through that. I can cancel through that. So that actually gives me mv squared is 1 upon 4 pi e naught q upon r. Alright, I'll stop there for now. Now the other piece of A-level physics we're going to use, we are going to use wave-particle duality. And de Broglie, or de Broccoli, to actually work out what's going on. And we're also going to use the concept of superposition of waves, and the idea that we can actually get standing waves. And we're going to use that to look at exactly the same problem and try and figure something out. So first off, what we've got again then is we've got this positive nucleus, and around it, at some magical distance, is an electron. Now, that electron is actually also a wave, so it's going around and around and around and around and around, back and forth as it goes. Now, the difference is that this wave is actually doing that around this orbit. Well, there we go. Like that. Now you can see it's done a complete. Now it hasn't actually lined up if I look at it, which is good. So I just picked a random kind of wavelength, and you can see that this wave is kind of not quite matching up in terms of wavelength. Some places it's destructively interfering. It doesn't exist there, kind of weirdly. Other places it's constructively interfering, so it really doubly exists over here. Now that model just can't exist. For us to have an electron in a stable orbit, we need this thing to be forming a standing wave. Right? And we need to have a standing wave running all the way around in this orbit that exists and is stable. So there are a few ways I can make that happen. First of all, if we look at it, so again what I'm going to have now is there's my nucleus, and around there's my electron, whizzing around in its orbit. And the first scenario that would be stable would be if it took a whole wavelength to get all the way around. So what would happen is it would be above, and then it comes down in under, goes down in under, and comes up. So the whole wavelength, there we go, there's my wave, but it's actually over the whole circumference of the circle. So that's 2 pi r in terms of the distance it has to travel. So that means I've got one wavelength, and that one wavelength is covering a distance 2 pi r. The next scenario that this could happen under, we've got here, and there's my magical radius that's actually going to be operating at. Now this radius, the next scenario that's going to give us a standing wave is if I have a wave that comes around, then goes under, then goes above, then goes under. So what I've really got now is a wave that does this, where that whole distance is 2 pi r, because it's taken 2 whole wavelengths to get around. And it will just keep going around there quite happily. Third scenario then, we're going to consider. So 3 wavelengths. Probably guess there's a pattern here. I'm going to look at this. There's my radius. Now my I've got to have 3 wavelengths. So I've got 1, 3, 4, 5. So 1, that, there. 1, 2. 1, 2, 3, 4, 5, 6. I've drawn it a bit badly, but there we go. So I go above, underneath, above, underneath, above, underneath. So in this case, my whole distance, 2 pi r, would now be 1, 2, 3 wavelengths. And there's a scenario coming here, as you can see, where this is n lambda, in terms of n number of whole wavelengths to make a stable orbit. Now, let's have a little bit look a little bit closer in terms of what's going on. So first off, what I've got here is that lambda must be equal to 2 pi r to make this work. Here I've got lambda, 2 lambda is equal to 2 pi r. Here I've got 3 lambda is equal to 2 pi r. And my general case then is n lambda must be equal to 2 pi r for this to work. Okay, now what does this actually mean? Well, this is actually n as I work through it. So what we're saying here is lambda is 2 pi r upon n. Here lambda is 2 pi r upon n. Lambda is 2 upon n pi r. So you can see again the pattern that exists all the way through, which means I can validly write 2 upon n pi r is my general equation for lambda as I go. Alright, okay, so now what I've got is I've got an equation for a wavelength. But de Broglie gives us a little bit more information. Now de Broglie tells us that my wavelength must be equal to Planck's constant divided by the momentum, which I can write as Planck's constant divided by the mass times by the velocity. Right, I'll move it up a little bit. So we've got Planck's constant, my wavelength is Planck's constant divided by the momentum, which is Planck's constant divided by the mass times the velocity. But I now know my wavelength is this. So I now know that that must be equal to 2 upon n pi r. So I can rearrange and actually get my velocity. So if I rearrange my velocity, I'm going to get that we must have rearranging for my velocity, sorry, I must have a point where I've got nh is upon 2 pi mr. So my velocity is nh upon 2 pi mr. Okay? So, kind of interesting. We've now got a definition of the speed the electron must be moving at, and it's at discrete speeds. It must be at n times by h upon 2 pi mr. So it can only exist at certain speeds. Alright, so what can we do with this? Well, if we go back, you can see we've got mv squared is equal to this. So let's trig that around a little bit, and that means that I can say that v squared is going to be qq upon 4 pi e naught mr. So I've got v squared is equal to that. But over here I can now get v squared as well. So I know from here that v squared must be equal to n squared h squared 4 pi squared m squared r squared. So this must be equal to this. This is working on the basis that it's a particle undergoing Coulomb's law and circular motion. This is working on the basis that it is the electron's a wave, and it's got to be following a Pauli superposition such that we get a standing wave. But the two cases must exist. Just one because it's a wave, and one because it's a wave, and one because it's a particle. So let's say that qq upon 4 pi e naught mr must be equal to n squared h squared upon 4 pi squared m squared r squared. Ooh, let's see what we can get rid of. Some of this has got to go away. So let's get rid of r and that squared there. We can get rid of that m, and we can get rid of that squared. The 4's can go. And this pi I can cancel with that squared there. So that actually gives me qq upon e naught is n squared h squared upon pi m r. Okay, running out of paper here. I've got qq upon e naught is n squared h squared pi m r. Now the whole point of this is, can we find where these electrons, or this electron that we're talking about at the moment, is in orbit, and we want to know r. We want to know how far away is it from that nucleus. So we've got to that point, and what I'm going to do then is just jump over. Oh, sorry, I'm sorting out all the papers. There we go. So if I rearrange this, what I'm going to get then is I'm going to get r is equal to n squared h squared e naught, n squared h e naught, divided by pi m q q. So we've actually got something, constant, pi, and mass of the electron, the charge on the electron, the charge on the nucleus. In fact, looking at this, I can write it as n squared h squared e naught pi m q q, where n can be only integer values of 1, 2, 3, etc, etc, etc. So what we've actually done is we've worked out the specific radii for this scenario that we started with. Alright, so everything so far we've basically done, and we've made generic. I've put no numbers in, I've put no other constraints in other than we said at the start. So let's see what this actually means. So I'm going to take this, and let's go back to considering hydrogen 1, our simplest atom we can really have. It's going to consist of one proton in the middle, and around that, normally in the ground state, would be one electron. Minus 1e plus 1e. Okay, and this distance there, we have said, is a distance r. Right, because n is equal to 1. Now, the question is, what is this? Alright, so for hydrogen, we're going to plug the numbers in. So my r is equal to, I'm going to leave the n squared in. That therefore is going to be equal to n squared. So then I've got times by